Today we're going to be finishing Chapter 10 with Section 10.3, which is testing the difference of proportions. So in this section, it's going to be very similar to the previous sections where we're testing the difference between two things, whether it's two means, whatever. This time we have two independent binomial experiments. And not only are they independent, we've already worked with independent samples. Now those proportions have outcomes that are in no way paired with one another. So the two outcomes cannot be mapped one to the other at all, testing different things. For example, in the book, it opens with the proportion of people favoring more wilderness areas different between men and women, or behavior between young people and old people. Two different groups of people that we are testing the difference between. For this section, we're not going to introduce many new things, just variables that we've already learned organized a little bit differently. So we have point estimates for our two population proportions, P1 hat and P2 hat. P1 hat minus P2 hat is just going to be the number of successes for the first over the number of trials for the first, minus the number of successes for the second over the number of trials for the second. This is just an expansion of the equation of this by itself. We're also going to have a new definition for the mean, mu. The mean is going to equal P1 minus P2, the proportion of the first data set minus the proportion of the second data set. And we also have a new equation for sigma, which is equal to the square root of P1, this is the probability of success, times Q1, the probability of failure, divided by N1. And we're adding to that P2 times Q2 divided by N2. Now, since we have a way of calculating sigma, you can probably guess that this thing is going to be approximated by a normal distribution. We will talk about that more in a little bit. This is a plus sign. Now, a new variable that we're going to learn is, let's draw a dividing line, is P hat. Sorry, no, pooled P bar. P bar, which stands for the pooled estimate of proportion. It's written like this, and it's going to be equal to R1 plus R2 over N1 plus N2. Now the reason why this is important, it says this in your reading and you can read this, but eventually when we start doing tests, our null hypothesis is going to be that P1 is equal to P2. And since we don't know the values of P1 and P2, they're unknown, we generate this this variable P bar to stand in for P1 minus P2. So previously we would not be able to calculate this equation missing P1 and P2. Now we can plug in P bar, and since we can find P bar, we can also find Q bar, which is it's not a Q. That is also, how do I draw a Q? That is a Q. Q bar is the chance of failure, which is just going to be 1 minus the chance of success, P bar. With this new variable, we can create a new equation for our test statistic. Z is going to equal P1 hat minus P2 hat. We will be given the data to be able to calculate that. and that's going to be divided by the square root. It's going to be our sigma. We're going to rewrite it how we wrote it here, and we're going to say P bar times Q bar over N1 plus P bar, let's rewrite that P, times Q bar over N2. This is going to simplify the equation for sigma because this is an easy thing to calculate, and these variables are going to stay the same here and here. Since we are using the normal distribution to calculate this or to approximate it, the same rules must apply, and that is N1 times our new variable P bar, N1 times Q bar, N2 times P bar, and N2 times Q bar all have to be greater than 5, larger than 5. And that is coming from section 7.6. That's not a new thing, that's just we need our sample sizes to be large for this binomial distribution to be approximated as a normal distribution. Now that we've laid some groundwork equations, you can read over the procedure on page 439. I'm going to go ahead and start example 7. And in example 7, we're not doing anything new. This is all the same stuff that we have practiced for several sections now, just done a minorly different way. So, the Mesa County Clerk wishes to improve voter registration. One method under consideration is to send reminders in the mail to all citizens in the county. This is on page 439, if I didn't say that previously, who are eligible to register. As part of a pilot study to determine if this method will actually improve voter registration, a random sample of 1,250 potential voters was taken. This sample was then randomly divided into 2 groups. So we have group 1. Group 1 has a sample size of 625 people. No reminders were sent to register. No reminders to register were sent to them. The number of voters from this group who registered, we're going to consider that a success for this experiment, was 295. So our R1 value is 295. We have a second group, group 2. It also contained 625 people. Reminders were sent in the mail to each member in the group, and the number who registered to vote are 2. Our successes were 350. We can tell this is the difference of 2 proportions because even though in this particular example it's the same body of voters, the body of voters are, so one was sent a reminder, one was not. And we're seeing, is the reminder an effective way of increasing voter turnout? The county clerk claims that the proportion of people who registered was significantly greater in group 2. On the basis of this claim, the county clerk recommends that the project be funded for the entire population of Mesa County. Use a 5% level of significance to test the claim. So our alpha value is 0.05. I apologize for stumbling over my words. It is currently 2 a.m. at the time of this recording. Now that we've determined these things, we can calculate a couple of our variables such as P bar, but first let's determine the test, the type of test that we're going to be doing. So just as a basic rule, something that's always going to be applicable to this section, the null hypothesis, H naught, is going to be that the 2 proportions are the same, and that means P1 minus P2 is equal to 0. what we want to test in this particular test, our alternate hypothesis is the reminder effective? Basically meaning, is the chance of success in P2 greater than P1? That can be written as P1 less than P2, but you might also seen it written as, and I'm going to write a little slash here to say that these are different. It could be written as P1 minus P2 less than 0. And written this way, we might get a better understanding of what type of test we're running. Since we are looking for less than 0, we can tell that this is going to be a left-tailed test. So now let's calculate some things. To calculate the test statistic Z, we're going to need P1 bar, or P1 hat minus P2 hat. And we could have calculated these things individually by taking R1 over R2 and then just setting that beside R2 over R1 over N1, R2 over N2. And this is just combining the step. So our Z statistic is going to be calculated by our R1 is 295. That's going to be put over 625. We're subtracting from that 350 divided by 625. This is the top of our equation. But before we can divide it by the standard deviation, we need to calculate p hat. And from that, calculate q hat. Not hat, bar. P bar, q bar. Okay. So p bar, we're going to use this equation over here to calculate it. R1 is 295 plus R2, which is 350. And dividing that by our total sample size, that was 1250. We were told that in the beginning. So our value of P bar is 0.516. And with that, we can go ahead and calculate Q bar. It's going to be 1 minus P bar, and that value is 0.484. And with these, we can finish calculating our test statistic. So our standard deviation is going to be written in as the square root of P bar, 0.516. This is a parenthesis, times Q bar, which is 0.484. My periods kept getting erased. Divided by the sample size of 625. And we're going to add the same thing. So basically, we're taking this and for this particular equation, it'd be multiplied by 2. But our sample sizes aren't always going to equal one another. Ours just happen to be split down the middle of the total population. So I'm going to write it out again, not to write anything confusing. Over 625. And this test statistic is going to equal negative 3.11. With this, we can turn to our tables, our area of standard normal distribution table, and the value of P for negative 3.11 is 0.0009. So the p-value of z less than 3.11 is 0.0009. Since this is a left-tailed test, this is the value that we're looking for. That's so weird. The periods that I'm writing keep getting erased, and I don't know why. Now that we've calculated a p-value, we do the same thing that we've always done. We're going to conclude the test by comparing the p-value to alpha. The p-value here is much smaller than our alpha value, and that means we reject the null hypothesis. And the interpretation of that would be, at the 5% level of significance, the data indicates that the population proportion of potential voters who registered was greater in group 2, the group that received the reminders. So now that we've run that test, we're confident that our funding is going in the right place, and we should send out reminders to voters before an election happens. The last thing we're going to do in this section is a confidence interval example in example 8. This is going to be a shorter lecture because it's really stuff you've already learned. This is stuff we've been doing. There's nothing really new about it. The equations look a tiny bit different. We're going to have a new equation for our margin of error. We have to use an approximate standard deviation in this type of test. This approximate standard deviation is going to be sigma hat, but the actual calculation isn't going to be very different. So sigma hat is equal to the square root of p1 hat times q1 hat over the sample size 1 plus p2 hat times q2 hat over the second sample size. The same pretty much that we had over here, just minorly different, now using the point estimates for p and q instead of the just the regular, like the actual probabilities. Our margin of error E is going to be calculated with a similar equation as before, the test statistic ZC multiplied by our standard deviation, but this time it's going to be sigma hat, the point estimate for our standard deviation. So let's do example 8 where we test it out. I'm going to skip the story and I'm just going to read the problem statement. Suppose that 2 groups of subjects were randomly chosen for a sleep study. In group 1, before going to bed, the subjects spent 1 hour watching a comedy movie. In this group, there were a total of N1 equals 175 people, dreams recorded, of which 49 were dreams with feelings of anxiety, fear, or aggression. So chance of success or a positive hit in this test is going to be a bad dream. And there were 49 of them. In group 2, the subjects did not watch a movie, but they simply went to sleep. In this group, there were 180 people who had dreams, and of those, the chance of success for having a bad dream was 63. So, before we can calculate a confidence interval, we need to calculate some things such as P1 hat and P2 hat. This is just going to be R1 over N1, that is 49 over 175, which is 0.28. We need to calculate P2 hat, We're going to do that the same way. It's going to be 63 over 180. That value is 0.35. And we can find Q1 hat by taking 1 minus P1 hat, that's going to be 0.72. And Q2 hat is going to be 0.65. With these, we can calculate a sigma hat. Let's do it individually because sometimes sigma hat is useful for a number of calculations, so it's good to calculate it individually, then plug the value into other equations. So we're going to take the square root of 0.2. Why is that happening? 0.28 times 0.72 divided by the first sample size of 175, and we're adding to that 0.35 times 0.65 divided by the second sample size of 180. We can test that the sample sizes are large by running the n times p. It checks out. The value of sigma hat is going to come out to be 0.0492. We want to run a 95% confidence interval, and the z-score for a 95% confidence interval is 1.96. That can be found in the back of the book, which means we calculate our margin of error E to be 1.96 times 0.0492, which is equal to 0.096. Now that we have a margin of error, we are going to add them to the difference of the point estimates of our chance of success. And what that means is, so basically we're forming a confidence interval for P1 minus P2, which means we would take the point estimate P1 bar minus P2 bar, and we would add plus or minus E, the margin of error, to find a confidence interval for P1 minus P2. We've already calculated P1 hat and P2 hat. P1 hat minus P2 hat is negative 0.07, I believe. Negative 0.07, which means the lower boundary of our interval is going to be negative 0.07 minus 0.096, and the upper interval is going to be negative 0.07 plus 0.096, which is, in ordered pair form, negative 0.166, comma 0.026. And the way to interpret this is we are 95% sure that the interval between negative 16.6% and 2.6% is one that contains the percentage difference of bad dreams. And we can draw conclusions based on this the same way as before. This is a shorter lecture because we're not teaching anything new. This is just the same testing of different data sets that we've been doing. The homework for this week, I'm going to send out test 9 for you to do. And we're also going to be doing the book problems 10.3, 1, 2, 4, 5, 7, 9, and 14. So, test 9, which I'm going to make and send to you. It should be attached in the same email that you received this video in, and these homework problems. Have a good week, and happy Easter.